is Karim Usama, and I'll be speaking about our first topic 3D printing and rapid prototyping with usage in space stations for advanced production technology module. Industry 4.0 promises a revolutionary mode of manufacturing. There are inherent risks that must be accounted for, like widespread deployment and usage of cyber-physical systems. These risks must be factored into manufacturing costs and will forever pose a challenge and a practical problem to manufacturing system. Now we are getting to the 3D printing or additive manufacturing. A three-dimensional printing is a process by which an object or part is fabricated directly from a digitized mode. The application of modern processes like 3D printing and rapid prototyping will be examined finally through utilization in space stations. Now for the utilization of 3D printers, it's a modern 3D printers are an increasingly widespread superior alternative to traditional machinery due to their various capabilities. They can copy and print designs legally as they are part of the Creative Commons, which makes the works of other people available for further use. And the Creative Commons is something related to the legal aspects, and this is especially true if the designs are built for individual or small volume usage. However, it must be noted that in most countries, patent laws exist that give creators sole permission for mass production and commercialization for 2 or more decades. There are also products such as guns that are explicitly prohibited from being made due to the lack of law enforcement's ability to track the ownership and the manufacture place. For now, the technology is relegated to prototype development and educational purposes, and thus there has been no widespread adoption of this technology by the general public so far. Now, for the 3D printing technology itself, we're having three factors: additive technique, the 3D printing technology, and what are the materials most widely used by this technique. We are having material extrusion, VAT photopolymerization, material jetting, binder jetting, powder bed fusion, and direct energy deposition, and sheet lamination. And each will be checking now. First part is the material extrusion. This is the process of material extrusion is done via the application of pressure and heat and the use of a die for the formation of a product or part. Extrusion is part of the manufacturing family known as bulk forming, which is itself is one of the deformation processes. The extrusion process is considered a hot working deformation process. Using the extrusion process in an additive manner allows for novel material extrusion methods in which the raw material of the final product or part takes the place of the work piece. For the purpose of 3D printing, material extrusion occurs when heating elements, electrodes, or laser beams transform deformed plastics or metals by making them molten, and then in a layer by layer deposition manner create new parts or products. Now for our second technique, vat polymerization. As the process is known, refers to the use of liquid resin that is hardened or cured when exposed to UV light, lasers, or LEDs. Typically, the resin is held in a reservoir in which a platform is placed to hold the part made of cured resin. The process of layering occurs in either one of the two ways. First one, the platform sinks the top layer of the part or product being built beneath the surface of the liquid resin in the vat and the resin is then cured. Or second method, the top layer protrudes above the surface of the liquid resin and then the bottom layer is cured. Stereolithography process involves the use of layered UV light tracing, which may be done starting from the bottom of the object or from the top down. Our third part, which is powder bed fusion, which is a form of powder metallurgy in which fine powdered materials are blended together, compacted, and then heated in a controlled environment on different surface areas to create parts or products. Products made by BBF are dependent on the physical and chemical characteristics of the powders they employ. BBF can be broken into three main processing technologies. The first is fusion with agent and energy, the second is fusion with lasers, and the third is fusion with electron beam. BBF method of 3D printing prints parts from the bottom up with the use of a laser to center or melt the powdered feedstock. material jitting, which refers to the layer deposition of liquid feedstock or raw material that is hardened or cured when UV light or heat is applied. Materials that can be deposited in this manner are wax, thermoplastic polymers, and low melting point metals, which can be combined in composites. According to 3D hubs, there are three 3D printing technologies that use material jetting: the eponymous material jetting, nanoparticle jetting, and drop on demand. Now for binder jetting. This 3D print technology involves the deposition of a bonding agent that binds thin layers of powdered material to create a part or product. The bonding agent is typically applied through an inkjet printer head at a specific location to build one layer at a time. The cross-sectional area of the layer that has not been bonded serves as support. The materials that are typically used as feedstock in this technology are ceramic or metal based. Now for the direct energy deposition, which is a 3D print technology that employs electron beams or lasers to melt metals in the form of powders or wires in a layered manner. This technology covers a wide range of methods for the disposition of molten metal layers: laser engineering, net shaping, LENS, direct light fabrication, DLF, and 3D laser cladding. And direct metal deposition are all considered part of the DED family, direct energy deposition. The DED technology has been around for a very long time and has been commonly used in the repair of surfaces or for the addition of extra material to an existing workpiece. In its traditional role, DED technology is referred to as welding. However, in its adaptation to 3D printing, it's undertaken in a manner that is similar to fused deposition modeling according to 3D hubs. Direct energy deposition comprises lens, laser engineering, net shape, and electron beam additive manufacturing (EBM). Now for the sheet lamination. It's a process that has typically been used to combine fibrous materials in varying orientations to produce a final product or part. The layered administration of fibrous substrates is done until the desired thickness is reached, after which curing takes place under pressure and heat. Lamination can be also done on sheets of metal. When fibers are being combined, they are typically bonded together by means of a resin. On the other hand, metallic sheets are bonded via ultrasonic welding or lasers. Fact, lamination is not a pure additive manufacturing technique because once the desired object has been created, unbounded fiber or metal layers need to be removed. This requires extraction of the part or product from the surrounding sheet material and thus requires specialized CNC machining in the post-processing phase. We are getting to the advantages of 3D printing. Flexible designs and rapid prototyping and print on demand. Print on demand is another advantage as it doesn't need a lot of space to stock inventory, which is very important nowadays, especially for supply chain channels needing to rent warehouses and things like that. For the advantages, we are having strong and lightweight parts. The main 3D printing material used is plastic, although some metals can also be used for 3D printing. However, plastics offer advantages as they are lighter than their metal equivalents. This is particularly important in industries such as automotive and aerospace, where lightweighting is an issue and can deliver greater fuel efficiency, as well as the fast design and production. Depending on the part design and complexity, 3D printing can print objects within hours, which is much faster than molded or machined parts. It's not only the manufacture of the part that can offer time savings through this 3D printing, but also the design process can be very quick by creating STL or CAD files ready to be printing directly. Our second part from the advantages is the minimization of wastes and being environmentally friendly. And this is very important to decrease the carbon dioxide emission rates. As this technology reduces the amount of material wastage used, this was a process is inherently environmentally friendly. However, the environmental benefits are extended when you consider factors such as improved fuel efficiency from using lightweight 3D printed parts. Now, as we spoke about the advantages, let's get to the disadvantages. We're having limited materials that can be utilized through utilization of 3D printing techniques. Restricted build size, we are only related to the size of the equipment, not as like the large CNC machines. Large volumes, 3D printing is a static cost, unlike more conventional techniques like injection molding, for example, where large volumes may be more cost effective to produce. What is the 3D printing future trends? Well, 3D printing for serial production, additive manufacturing is headed for very exciting times because it's gradually becoming mainstream. 51% of mega enterprises are actively using 3D printing for production. Uh, for the last year, BMW announced that it had fitted its 1 millionth 3D printed parts for its BMW i8 Roadster, reference 5. Actually, it was in 2018. Uh, the design of software for additive will become more integrated and easier to use, of course. There is a special program named Autodesk's NetFab, as an example, developed to work with 3D printing STL files. Dental will adopt 3D printing as a dominant production technology due to its ease of use and the ease for dental aligner molds. As 3D printing is linked to rapid prototyping, what's the actual benefits of rapid prototyping? It can be described as the fabrication of a 3D object from a digital representation directly to a physical representation. This type of manufacturing allows for the creation of products without the need for large upfront costs, which is very important. Lots of time or direct manual labor during creation. This type of manufacturing can be described as a toolless process because dies, molds, fixtures, or other such tooling are not needed. The strategic and operative aspects of rapid prototyping. The creation of a prototype is very important part of the design phase of a product's life cycle. Prototyping helps to reduce the time to market, detect possible flaws, and supports the adoption of concurrent manufacturing techniques. Rapid prototyping allows for the physical production of models directly from a computer model with little or no human intervention, which reduces the time needed to conceptualize and build a product before bringing it to market. The costs involved in the making of a prototype can be broken into four main components. The first one is one-time cost, the second is setup cost, the third is the processing cost, and the fourth is the whole production cost. Get to our core of this presentation, the space station's industry application. When planning a mission to the ISS, NASA's traditional approach has been similar to how one might prepare for a long camping trip. Bring everything because we are not going home again. Or, or so far, we are not going home as soon. For the current issues to support spaceflight emissions, NASA sends up about 7,000 pounds of spare parts to the ISS every year, says Tracy Bretter, as mentioned in the reference. A materials engineer at Marshall Space Flight Center. When you are 200 miles from Earth, after all, you want to make sure that you have all of your necessary supplies from bolts to cable mounts. While launch costs will decrease with a greater number of rocket manufacturers and an increased frequency of launches, sending a pound of cargo to low Earth orbit currently costs about 10,000 USD. How can we solve the issue of this much money spent over only 1 pound of excess weight? To lighten the load and reduce costs, NASA is using the ISS as a test bed to demonstrate a way of manufacturing the necessary parts in space 3D printing. What used to ensure safety? NASA's additive manufacturing efforts for the ISS have focused mostly on the 3D printing of polymers or plastics. The fused filament fabrication process, the technique used by many desktop printers, works well in microgravity, is safe to operate in a crewed environment, and meets the International Space Station's power, volume, and mass constraints. But how to become more efficient? Some plastics used on ISS are also recyclable, an important feature when considering efficiency and cost savings. One day, the foam and films used to package cargo could potentially become the feedstock for manufacturing. The 3D printing on ISS so far, NASA's in space manufacturing project begun at NASA Marshall leads the development of technologies and processes that will enable on-demand manufacturing capability as teams explore the moon, Mars, and other habitats far from Earth. 3D printing in zero-G technology. NASA used a 3D printer for 2 rounds of operations from 2014 to 2016. The project investigated the effects of consistent microgravity on multi-deposition additive manufacturing of a common polymer material. But how is the 3D printing process done in space? Using a fused filament fabrication like we mentioned in the previous slide, FFF, the system's nozzle feeds a continuous thread of plastic through a heated extruder onto a tray layer by layer to create a 3D dimensional object, settled like a hot glue gun. Analysis of specimens returned from orbit in conjunction with material modeling efforts suggested that microgravity did not lead to engineering significant effects on the polymer parts, paving the way for increased use of this technology in space. The Additive Manufacturing Facility in Space (AMF). The commercial facility from Made in Space is a multi-material 3D printer for polymers. AMF manufactures those high density polyethylene ULTM 9085, which is a high strength blend of two other polymers, and the ABS acrylonitrile butadiene styrene, which is the most common plastic material for 3D printing. and the focus of the original 3D printing in zero-G experiment can therefore build a part measuring up to 6 inches in length, width, and height. Now for our best part, which is the recycling in space. The refabricator unit is designed to print parts with ULTM 9085, which can then be recycled back into feedstock for further printing. A reuse capability enables NASA to close the manufacturing loop on long duration missions so that the feedstock for the printers doesn't have to be launched. Capability to process plastic materials such as polyethylene into filament for 3D printing is also present in 2019. NASA and the metal 3D printing. On Earth, the, referred, the preferred metal 3D printing method for aerospace is selective laser melting, but those are very large and have higher power requirements. Additionally, the powers are combustible, a respiration hazard, and would be difficult to manage and control in a microgravity environment. Then, ultrasonic techniques that use force and vibrations to join adjacent layers of metal foil, wire plus arc technologies that employ a welding process to deposit and diffuse subsequent layers of metal wire, and bound metal deposition type methods that use filament or bases of metal particles backed in a polymer binder as normal situation. What are the management insights and improvements? What is needed in the ISS? What's needed for space explorations? For example, electronics printing. Many of the components which malfunction or need to be replaced on ISS are electronics. Currently, NASA's printed technology team is fabricating sensors for various applications such as CO2, humidity sensing, and crew health monitoring, which will be 3D printed on the ground at first and then tested on ISS. Perhaps in the next couple years, those will be applicable for manufacturing in space. What's the futuristic roadmap? A larger project called the Multi-Material Fabrication Laboratory from TechShot Company will include a metal additive manufacturing process, furnace, and end mill for post-processing of the printed part, and an in-process inspection capability which monitors the part as it is being built. The Fab Lab is designed to occupy a full express rack on ISS. I know I have attached several videos which are very interesting to be checked. The first is NASA Science Casts f- for the in space refabricator we spoke about earlier, and the second is the Made in Space as well, launched by, by NASA, and the third is the 3D printing revolution from Dutch Field documentary, and the fourth is 3D printing is changing the world. So, thanks for your time and your patience with me, and I hope that I nailed it well. Stay safe. Thanks.